division that is composed of 3 teams, and I'm actually integrated in both of these teams, so the solar irradiance and radiometry team and the planetary atmospheres team. Okay, so first part of my talk, so let's go talk about this. And give a bit of, I think it's mainly common knowledge of mostly of the people here, but I would like to give a slight refresh of this, of what we know about Venus. So we'll be using some of this information later on. So Venus, in some aspects is very close to Earth in size-wise. It's also the distance to the Sun. Of course, it's closer. Its period is shorter, of course, but in size-wise, it's very close to the Earth. And that's about it, because if you're taking a deeper look at the Venus, we know that we have a very different atmospheric composition. So Venus is 96% of CO2, 3.5% of nitrogen, and the rest we have some trace gases here. The most abundant are SO2, water vapor, and the monoxide of carbon. Also, the conditions at the surface are very, very different from what we found on Earth. So we have a crushing surface pressure of 92 bars and a surface temperature of 735 Kelvin. So this is due to the fact that it's a greenhouse planet. So here are the profiles of the trace gases that we know are on Mars, and their vertical distribution. So it's very low quantities. We are talking in parts per million relative to volume here. So what about a very important feature of Venus? It's cloud coverage. So it's cloud coverage. There you have some very interesting photos here from recent missions from Akatsuki, from the Japanese agency, and from Venus Express, ESA. And this cloud coverage it's global. It's all around the planet, and it's stratified, so to say. So we have a cloud layer between 45 and 70 kilometers that is sandwiched in between some thinner layers of haze. Both the haze and the clouds, they are mostly constituted of sulfuric acid. We also have some water vapor there, but mostly sulfuric acid. And here we have only the temperature profiles. The temperature profile, this is the surface temperature is 735. But here when we arrive on these two diverging curves, so this is the temperature profile on the day side of Venus and the temperature profile on the night side of Venus. So they are a bit different on the mesosphere. Okay, so in terms of what are the landmarks of the Venus exploration? So they started in the 60s with the Soviet Union and the NASA, United States, launching a lot of missions to Mars. And actually, the first successful mission was the Mariner 2. It was the first successful Venus mission, also the first successful planetary mission, and they give us a very important scientific return. So we were able to know the Venus surface temperature and the discovery of this famous cloud layer, this omnipresent cloud layer. It was also a result from Mariner 2. From the Soviet Union, we had very important missions as well, with the highlight being the Venera 13 and 14 missions that in 1982 took the first and only photos on the surface of Venus. Okay. From the ESA, so there were much more missions on the NASA side. Magellan, they did a complete topography of Venus. From the ESA side, we have Venus Express, launched in 2005, and Akatsuki from the Japanese Space Agency in 2010. We're going to take a bit of look on. First look at the famous. So these are the 2 of the 4 photos that were taken. So for Venera 13 and 14, these are the landing sites. So in the Phobia region. And these are the photos that we have. So we have this yellowish color, some rock formation. So this color is due to the composition of the atmosphere. So far, these remain the only photos that we have at the surface of Venus. So this is very historical, important historical results. So I'll talk a bit about Venus Express. It's a mission that was also for which Beta had also an implication. Launched 2005. It was inserted on the orbit in 2006, and the end of mission was 2014. So it was the orbiting of the spacecraft. The main scientific objectives were the study of greenhouse effect, of the global dynamics of the atmosphere, and on the atmosphere, its evolution, its composition, and the role of clouds. They were also interested in looking at the volcanic and seismic activity. Yes, some key results of this mission. So we have Venus Express gave us a very deep, very comprehensive knowledge of the atmospheric composition. You can see here, all the trace constituents, their compositions as a function of the altitude. So above and on top of the clouds. So this is all the trace gases that we see at the beginning. They are represented here. They were obtained with these two instruments, PICA-SWAR above the clouds and VERITAS below the clouds. There were some more results that I'll not go into detail, but it revealed the vertical profile of the winds of the atmosphere, a complex structure of the south vertex. And a very interesting result is that it was differential in the topographic structures of relative to the Magellan mission in the 90s was revealed, and this led to the suggestion that the Venus day is increasing, because the structures there are some differences in their period. So this led to the suggestion that the Venus day is increasing of 6.5 minutes relative to the 90s. On the side of future missions, so NASA is preparing two missions, DaVinci Plus, that the main scientific objective is the study of rare gases on the atmosphere. So it will be an orbiter and a probe that will descend into the surface. We also have VERITAS. VERITAS is more close to the EnVision that I'll talk later. And there is so these two missions, there were tentative launches in the beginning end of the 20s, beginning of the 30s. Let's see how it goes. But we are very interested on this aspect of VERITAS redoing the entire topography of the planet. That will be the first one after Magellan. This will be important for the EnVision mission. And now, EnVision mission. So I'll talk a bit about it, scientific objectives, how we're going to attack the volcanism topic, specifically in the VenSpec-H instrument. So these are the main scientific topics that were in the essence of creating the EnVision mission. The history, why it's a lot in the comparative history, comparative to Earth. So was Venus once Earth-like? Where did Earth and Venus diverge? The history diverged. The activity will be much centered in the volcanic aspect and the climate aspect. So we will have a better insight on the measurements of the mapping of the gases that are present in the atmosphere. So for the volcanism on Venus, we'll make the reasonable assumption that they will emit the same volatile compounds as in Earth. So, and the most important of these compounds on Earth are water vapor, CO2, CO, and SO2. And on Earth, the most used compound to trace these volcanism activities is SO2, because there are no other natural sources. So it will be we would think it could be a choice on Mars, or on Mars, no, on Venus, but no. Actually, the H2O is the best proxy for as proxy for volcanic activity, because it has a lower background than SO2, around 30 ppm, and there's no the only sink that water vapor has is high on the atmosphere, around 38 kilometers. So HO2 it will be very important. Its variability, it will be very important to trace volcanic activity. So still some results from Venus Express. So I'm going to a bit back and forth to give an idea of what we're standing in terms of volcanic and where we want to upgrade our knowledge. So this is a composite of radar image from two instruments, radar image and the VERITAS image. And we see some VERITAS is made an emissivity map of this structure, of this volcanic structure here, are hidden mounts. And so the emissivity is higher here, which indicate that recent, by recent we mean less than 2.5 million years lava flows on this structure. Another indication of volcanism on Mars is the SO2. Now we are talking on the mesosphere, so above the cloud top. So the mesospheric SO2, mesospheric SO2 has been measured since the 1980s from the Pioneer. So we have here this nice time series from which you see the SO2 decreasing till around 50, from 400 to 50 ppm in the end of the Pioneer vision. This time series was retaken in 2006 with the VenSpec mission. So we see here a small increase in the beginning of the mission, and then another decrease until 2014, until the end of the mission. So it will be interesting to understand if this SO2, mesospheric SO2, is connected to volcanic activity. So knowing the transport mechanism between the troposphere and mesosphere, or if it is like a dynamical variability. So we can by establishing some parallels between between the Pinatubo eruption and on Earth, or the cyclic phenomenon of El Nino and La Nina. So it will be a very interesting to be able to complete this time series now, like 20 years, 15 years apart, but it still will be very interesting to see where we are now. This is a much more recent result. It's from last year, 2013. So as a team that analyzed data from Magellan mission. So they looked at some structures around near the mouse. So this is blown out here. So this structure, and two different passes of Magellan 8 mounts apart. They reveal some topographic differences that suggest that some fresh lava flows had been responsible for this change of surface topography here. So this is a very new, interesting result to follow up. Okay, so as I said, we need to look at the tracers of volcanism, and we need to look at where they are produced, so very near the surface. The issue of looking near the surface in Venus is it's due to its very opaque cloud coverage, global cloud coverage, that prevents us to look down, of course. But one feature of this cloud coverage is that there are some transparency windows in the near infrared. So these transparency windows, there are 6 bands, so 6 spectral bands, 85, 90, so they are here, the spectral bands. So they allow us to peek through the atmosphere at this specific wavelength. And here we have the depiction of this spectral transparency windows taken by the NER mapping spectrometer instrument of Galileo, that is on this band, on 2.3. that we see here. The brightest region are the gaps on the clouds, and the darkest region is the flux that still arrives to find its way through the surface to above the clouds and to be mapped by instruments on these wavelength ranges. Now we go to see what is expected which compounds are expected to be measured who. As I see, so the SO2, H2O, CO, all below the cloud X, and actually the interaction, the measurement of these compounds below and above the atmosphere will be done by these three instruments, so VenSpec-H, VenSpec-M, and VenSpec-Q. So it's a suite of three spectrometers that will measure at different altitudes and different compounds, but for which we also have some overlap. For example, HO2 in the troposphere will be measured by both VenSpec-H and VenSpec-M, which is very important from a calibration point of view. So the global picture of the vertical distribution and of these compounds will be very important to understand the sulfur cycle, the water cycle, and the volcanism and the climate on Venus. Again, I come back a bit on what are the main objectives of the EnVision mission. So the EnVision mission was imagined to have a good image of the planet of Venus from the core up till the upper atmosphere, and for that we did six different instruments were designed, were imagined. Each of them covering different altitude ranges, so to say, and here we see that the spectrometers VenSpec-M, H, and U, so they cover from the surface up till the atmosphere, and so we're going to look into detail now to the VenSpec-H spectrometer. The PI is Anne-Karim Van Daal. She's at BIRA, so she's head of the department, and we have here the two person on my thesis committee, Séverine Robet. She's the instrument scientist, and Justin is the program manager of this instrument. Just a bit some facts on the mission. So it's an M5 mission. As an M5 mission, it's part of this series of M5 missions that will be, actually it will be the last one to be launched in 2031. It's the medium-sized mission that, it's in this is a frame of medium missions with some of them per decade. We have the S, we have the L missions, and EnVision is on the M-sized mission. A schematic view of the instruments. So we see here the radars. In blue, VENSAR, SRS radar, radio science instrument, and the VenSpec-Spectrometer suite is here. So they are independent spectrometers, but they have someone in common, that is the central control unit, that is mostly electronic control of the common of the three spectrometers. So for what are the scientific objectives of VenSpec-H and how this relates to the design of the instrument? So this was the phase A design, so to say. So we wanted to detect gases that are related to volcanism and their variability. So should be looking at the night side, expecting very low levels. But also we wanted to be looking at some gases above the cloud region. So we want to understand well what we need in terms of spectral lesions, of spectral resolution, signal to noise ratio. Also important is the coverage over the coverage, the spatial coverage on ground, and repeatability over different orbits. And so we need a very sensitive detector, especially for the night side. So we're going to need a very cold detector. and this is the block diagram of the instrument. That maybe it's easier to see later on when I will present the instrument in a more in a 3D way. So this is the definition of the bands. This is the simulated day side, if you're looking at the day side of Venus, and the simulated night side spectrum. So we see we have a very faint night spectrum, but we want to still measure some species on the day side, especially H2O on the band 1, 3, and band 2. On the night side, again to relate it to volcanism. And actually, this is this photo here is a photo taken from Akatsuki infrared camera, and it relates very well to this plot here on the night side and day side radiance. We see a very faint radiance from the night side, and a very bright from the day side, that scatters a lot of the sun incoming radiation. So we want to measure all these species, so we have to define also a resolving power. But on top of the required species, we want to measure HTO, H2O, SO2, SO. We also have some bonus species like some these halogens, HCl, HF, and the OCS. Yeah. So a bit of detail on the species we want to measure, and on the specific spectral ranges that we want to measure, and which altitude ranges will be sensitive to. So we see that we'll be measuring H2O and H2O very close to the surface. This measurement H2O between 0 and 15 kilometers, so is the integrated on the integrated column, is the first measurement that will be done at this low altitude range of H2O. So this is a very important, very innovative aspect as well of VenSpec-H. And only one thing I wanted to draw the attention is to this split between band 2. So it is important to measure all these components simultaneously. Yeah? So we want the variability. So we want to measure the volcanic tracers simultaneously, especially H2O and SO2. And we can measurement in this wavelength range here. But the issue is that this wavelength range is bigger than a diffraction order. So we are splitting this diffraction order in two, which will complicate a bit the design, as I will show later on. So here we have design, and I highlight the main components. We see here VenSpec-H is an instrument that is built on between two different temperatures. So we have the warm section that is should be at 0 degrees, nominally at 0 degrees Celsius, and the -45 section, and at and the cold section at -45 degrees Celsius. We have some elements on the warm, some elements on the cold section. It is important. So we have here the filter wheel that will select the spectral bands that we want to measure. And here is the filter slit. We have some additional filters on this, and this will be able to separate between band 2A and 2B. So we'll be imaging on the detector on two different strips. The grating and the detector will be the detector window. So we want to have as low as thermal background as possible on the that's why we keep a lot of the spectrometer section on the cold part of the instrument. So this is part of my work related to VenSpec-H. So it's to develop the instrument model. This instrument model, it consists of having a radiometric definition of the end-to-end from the entrance, from all the optic path till the detector. So this requires having knowledge of all the parameters that are part of the optical design of the instrument, the transmissions, the solid angles, the filters, rejections, the filters characteristics, the cut-on, cut-offs, the rejection properties, knowing the grating detector, knowing their sensitivity to temperature, and knowing also understanding well the detector characteristics, its noise, its gain, its linearities, so we are able to produce from having as input the simulated signal that we will receive on the instrument, be able to reproduce the instrumental signal that we would obtain, and this will be used to SNR to have a better assessment of the SNR. We need many inputs as strelights. For the detector, the readout modes, the observation strategy of the spacecraft, the operation. So all these aspects will be a big part of my work. So it is to develop a global radiometric model to understand finally what would be the accuracy of the retrieval of the molecules that we want to measure. So this is done in collaboration with my other colleagues at BIRA, Severin, Justin, and Ian. Okay, and now we'll be approaching. We're going to look why we want to see Venus as an exoplanet. How are we preparing in terms of future mission to look at this kind of planets? As well as in radiative transfer tools, where are we, what is the state of the art, and look into a bit the cloud issue. So this is the current status of the exoplanet detection. So we see here the distance to the star and the planet mass expressed as a function of Earth masses. I have here Venus and Earth, and I made a small region here where we could say that we are in a rocky planet detection zone, and we see that this area is very low populated. So we have 10, 20 planets on this zone, and most of them, if not all of them, except for Kepler-47c, have been discovered by microlensing techniques. So we have no access to atmospheric to no atmospheric knowledge whatsoever. So this is something that is being tackled on in the sense of developing. No, before that, I will look at why is important. What are the synergies between exoplanet science and Venus science? So solar system Venus and exoplanet Venus science. So this is some main conclusions from a review paper from last year. In which the main lines of research on looking at Venus as an exoplanet are stated. So what does Venus teach us about the evolutionary pathways of exoplanets? And is the evolution of Venus typical of Venus-sized exoplanets? So these two questions, they are twofold, in the sense that exovenuses may inform us on ancient and or future states of the evolution of Venus, and the current state of Venus could also help us understand better if we find Venus analog, what would be what could we learn from that. And within these big research lines that were underlined here there are some specific, more specific topics. So one is to measure the composition of noble gases and other key elements in the atmosphere of Venus. So this is very related to all these missions that I presented before, as well as determine the properties of terrestrial planets that would be observable on exoplanets. So it's to gather the most information in terms of observation and in terms of radiative transfer tools that can be transposed to the exoplanet observation of rocky planets that is actually being prepared. So it's something that is on the rails. So with ELT METIS that will be installed within this, still in this decade, on the extremely large telescope. So this is an instrument that has strong implication of the KU Leuven. They've been implicated on the science case, on the definition of science case, on the instrumental concept. Now they are very much involved on the operations, on the control of the instrument, and the LIFE. So LIFE, it's a space instrument, so it's a much farther horizon. It's to be from some decades in the future. So it's a nulling interferometry in space. So this will be it's a much more far horizon project. So I'll be looking a bit into ELT and looking what are its instrumental features that could be interesting to look at rocky planets, at exovenous Earth-like planets. So we see here a simulation of the METIS end-to-end high contrast simulator for Alpha Centauri 2. If Alpha Centauri 2 has two rocky planets, that would be a 0.55 AU and 1.1 AU away. We would serve them with this SNR, so 10 and 6, for the N2 filter that is situated for which the central band passes 11.2 microns. So it's the imager and plus coronagrapher sub instrument of METIS. So we will be hopefully very soon be able to gather information of exoplanets. And when we have this information, we should be we should also have the tools to understand what are we looking at. So this is a part of the bibliographical work of this PhD project, and it has been remarked by some authors in the latest years that we might be running short in the robustness of the models, of the radiative transfer models, with respect to the data quality that we're gathering from the observations. Also, we might be oversimplifying some the parameterization of clouds. So we have to advance in the parameterization of clouds, because this may be a limiting factor in some. We are considering too simple of cloud models on the radiative transfer model side, and that will be as well a part of my thesis work. So it is to gather information from some radiative transfer codes. So in this case, Petit Rat Trans. So Petit Rat Trans is a recent code developed into a user-friendly Python framework, very easy to use, and that we want to compare with Azimuth. So Azimuth is a code that has been originally developed for solar system observations for Mars, for Earth, and for Venus. So we want to understand if there are some advantages in comparing both codes, in the sense that Azimuth brings us a parameterization of clouds that is it's very much it's more complex. So, for example, I come I take the example of the Venus cloud. So there is a substructure on this cloud. So we have the ASUS, the clouds, and the overlying and the upper ASUS. But within these clouds, there is there are different size particles, different densities along altitude, and this is something that we can simulate in azimuth. It's not the case for petit ratrans as well. So we wanted to see how well does a simple case of clouds is able to compare to a more complex parameterization. So we can look at the more complex parameterization, but we were also interested in maybe concatenating this complex parameterization in one cloud layer. So we were looking at this possibility as well of having different clouds with different parameters, different cloud types with parameters, asymmetry parameters, scattering parameters, size, cross section, and concatenating this into one cloud, one type of cloud that would embark all these parameters, so it will be a part of the validation of models. Yeah. So this work is an ongoing work, and it will be part of one abstract that we submitted to present as poster in the next exoplanet conference in June in Leiden. Yes, that's it. Thank you.
Thanks, Nuno, for an interesting talk. Time for questions. Yep, start with Dario.
Thank you for the talk. I was wondering, what is the origin of the volcanism on Venus? Because I assume there are no plate tectonics.
There's no plate tectonics.
So where does the volcanism come from?
The volcanism, you can have hotspots, not necessarily plate tectonics. I mean, the plate tectonics, they create volcanoes on some subduction zones, but you can have hotspots as well.
Okay, and there are so many hotspots.
Yeah.
Okay, thanks.
But you have hotspots on Earth as well.
Sure.
Like,
Hi, thanks for the talk. I'm sorry if I missed it, but so you were talking about day side, night side, but what's the coverage in terms of like equator versus the poles? Does the orbit of the spacecraft allow for you to cover the other areas as well in terms of characterizing the atmosphere?
So it will be, let's see if I have a map here. No. I don't know the details of the operation of the spacecraft, to be honest, but it will be.
Do you know its inclination?
It will be. Sorry.
Do you know its inclination?
No.
Oh, okay.
I'm gonna look. I can look into it for you.
But it's not just covering the equator. You'll see very.
No. It will be. It will be like inclinated orbit. Yeah, it will not be around the equator. It will be an inclinated orbit. Of course, we want some spectral coverage, so we want to be able to raster the planet in this sense.
Okay, cool. And then a second question: do you expect there to be significant variations across that part as well, aside from just day side, night side?
In the Terminator?
Yeah.
Yes, there's a question that some colleagues of mine will address, the Terminator. And there, I don't think I have. We saw this with Venus Express, but I don't want to adventure much there because I'm not the best person to comment on this. But I have some plots here I can show you after also.
Okay, thank you.
Thanks for the presentation, Nuno. You mentioned for the instrument model about stray light. What types of stray light are you considering, and where would they be coming from?
Okay, so on stray light, wait. So we have stray light because actually we are we have a spectrograph, but you have all the orders that are coming into the detector. You filter them, but you still have some. This is not a zero transmission,
Okay,
so you still have some.
So out of band.
You have that stray light. You have this is called the out of band stray light. You have out of order stray light. You have out of band stray lights. You have spatial stray light. So there's different contributions. And there's contributions that you can only know by optical design. So this is the partners that do optical design. It will be a work package dedicated to understanding the spatial stray light on the detector. I'll be working mostly with the stray light that comes from adjacent orders. All the orders actually. It's kind of an interesting problem because, for example, you have stray lights from these orders here.
Yeah.
Because you see the dynamics of the signal is quite high, so we have to really worry with the stray lights. It's a problem. The stray light is coming from here.
Yeah, it will dilute your features. Yeah. Okay. Yeah. Thanks.
I think what you're describing there is not stray light, but spectral leakage. I mean, it's so you say that you in the wavelength at what is it 2,400, you see the spectrum of 1,200 superimposed. That's probably because you have a higher order spectrum.
Yes.
That is not filtered out correctly.
Yeah.
But I think the question of Yannis was stray light is normally that so out of in the spatial direction, yeah, or light that doesn't come from the part on Venus that you're trying to take a spectrum of.
Yes.
That from a mountain next to it, so to speak, light is entering and landing on in a diffuse way on your detector,
yes.
Which is difficult to understand because you have this slit. So I think that was what Yannis was. It's not clear what the origin is.
We can define maybe a bit better the terms in terms of stray light is something we define it as something that we don't want on the detector. So it's everything that is spectral leakage or adjacent orders, high orders or lower orders. Yeah.
So I have a question, which is two questions actually. One which is a detail on the next slide. But first, on this slide, you show that during the daylight you have much more flux than on the night side, which is expected. But on the next one, you show that there you write in band 2 you have a higher signal to noise ratio on the night side. So where does that come from?
It's because we are binning. That's a good question. There might be an issue with these numbers. Sorry.
Okay. Anyway.
No, it's
that's fine.
It's
It was just wondering when I saw this if you change observing mode or something.
It's probably an old table. I have to revise this table.
Then I have another question, which is on you indicated that there are, if I understood correctly, hints on a slowing rotation of the planet since the 90s, which is quite massive. So my question is, given it's a retrograde rotation, wouldn't you expect actually an acceleration of the rotation to synchronize with the sun? So wouldn't you expect an acceleration? And of course, do we understand why there could be a deceleration? And the parallel question is, with the radar observation, will you be able to assess this during the lifetime of the mission?
I cannot really answer this question.
Okay.
But I think you have a kind of a hint, no?
Sorry?
You have something.
No.
An element?
It's
no, I don't know.
It's a question.
It's no.
Okay.
More questions? We have plenty of time. Don't be shy. In the meantime, while people are thinking, I'll have a question myself on the synergy or connection between Venus and exoplanets. So you've opened that topic with the question, like, can we use our knowledge on Venus to extrapolate, right, to the evolution of exo-Venuses? So my question is actually, can you do that, given that Venus itself is found in how we understand it right now, at least, in a pretty unique star-planet system, so in the solar system. So there are a whole bunch of other planets that are influencing the evolution of planets. We have Jupiter somewhere far, far away, right? Whereas around the other stars, we find a lot of hot Jupiters.
Yes.
Can you really extrapolate whatever you learn about Venus to other star-planet systems, given how unique the solar system is?
I think that it's you might be in the providing that we found very similar. Very similar configuration of distance to star and mass configurations.
But
the probability should be low.
Don't you think that other planets are also influencing the Venus-like planet around some other star, for example?
They are
Don't you think that other planets in the system have also impact on the evolution of Venus?
On our system.
So essentially what, at least the way I understood it, you want to study Venus in a scenario where it's basically the only planet around the sun. And that's how you want to extrapolate whatever you find to other stars. But unfortunately, or fortunately actually, Venus is not the only planet in the solar system. Yeah. So I guess somehow the effect of other planets needs to be taken into account. No?
Of course, I think when you talk about Venus, it's I think we should enlarge it to rocky planets. It's not only Venus that we are interested in. So it's rocky types of planets.
Okay. Yeah, Danny.
How do you feel about the supposed phosphine detection, and will this mission put the final nail in that coffin?
I was not expecting that question, so I don't have a slide for that, an extra slide, or maybe I have. So the original phosphine detection, it was. So this is like a time series of what happens, and it's resumed here by this is a colleague of mine at Bira, Loïc Trompé. So he made like a good resume. He also used the Venus Express data to give his contribution to the discussion. So it was first detected at 20 ppb by the Griffiths in 2020. Then ENCRNAS 2021 put the after detection limit of 5 ppb with this instrument, with Texas instrument. Yeah, and then she at some moment she revised her provisions to 1 ppb, so it's already a big bump. And Loïc Trompet, my colleague, so he was looking at this band here, and put upper detection limit of 0.2 ppb, which is 100 times less. So if we detect phosphine, it would be below this limit and not at 20 ppb. So this is a bit how the discussion evolved. And now if you ask me if we are prepared to detect phosphine with EnVision, we are not. Because actually the discussion, it came already in 2020. The instrument was being developed, phase A was on rolling, And we don't have spectral coverage, so we don't go so far in the near infrared to be able to have some lines of phosphine here. So I think this is the latest article in this series, and if it puts so you need to really go low in sensitivity to be able to match these detections. But so far we didn't detect phosphine on Venus.
All right, thank you.
We have time for one more question. If somebody wants to ask a question or make a comment. No? Okay, let's thank our speaker again. Thank you. Thanks for coming and see you next week.